carrying on the look at locus and complex numbers. But this time we're looking at functions. So omega is some function of z. And then we'll be asked to find the locus. It might be of omega, it might be of z. It might be either one. And they'll usually give us some condition on either the one of the two. The trick to this is whatever the condition they've given you, try and make that the subject. And then you work with that. Now, some common ones. They often say something like this: oh, omega is purely real. So what can you do with that? Well, there's two things you could do. You could go algebraically and go, well, that means the imaginary part must equal 0. And you go and play with that. Or if you think about it geometrically, you go, well, hang on, that means the argument is either 0 or pi. And that can help you out in the problem. The other thing, of course, similar to that, is they might say it's purely imaginary. In that case, you'd say, well, the real part's equal to 0. Or the argument's equal to plus or minus pi on 2. This one here, if you see argument, and then you've got like a fraction, and it's a linear function on a linear function. I don't know, z plus 2 on z minus 3, or something like that. That's going to end up being an arc of a circle. We know it'll be a minor arc if that angle is bigger than 90. It'll be a major arc if it's less than 90. And of course, if it's equal to 90, you've got a semicircle. So there's a few to look out for. Something like this. We've been told the function is w equals z plus 2 over 2. I'm just thinking whether that's a typo and it should be z plus 2 over z. Or c anyway in my working out. But the condition we've been told is that the modulus of z is equal to 4. So that's the thing we know. So we want to make z the subject. Ah, yes, it was. It was a typo. It should have been z on the bottom there, not 2. I thought so. Okay, let's rearrange it and make z the subject. Eventually, there it is. Z equals 2 on w minus 1. Now, why do that? That's the thing we've got the condition for. So I can now say, well, I know the modulus of z is 4, so that means the modulus of 2 on w minus 1 is equal to 4. So now I can work out what's the locus of w. Well, as it stands at the moment, it's not immediately obvious, but if I play around with it, absolute value of 2 is, of course, 2. Turn both sides upside down and also move that 2 over as well. We'll get that the modulus of w minus 1 is equal to half. Now that's something I recognise. Modulus equals a constant number. I know I got a circle. So it's a circle. The centre's at 1, 0. The radius is a half. That would be its equation there. Try this one. This is one of the ones where it's purely real. So locus of z in this case, w is z plus 1 on z minus 1. W is purely real. So w is already the subject. Now I said there was two ways we could do it. If I treat it algebraically, so I drop everything into x and y's and see if I can come up with an equation. Well, I want to realise the denominator, so I'll multiply by the conjugate. So on the top I get, well, this lovely expression, x squared minus 1 minus I times x plus 1y plus I times x minus 1y plus y squared over conjugate, so it's the sum of two squares. We get x minus 1 squared plus y squared. I'm not going to bother expanding this all out because the condition is that this is purely real. Now, if it's purely real, then I know the imaginary part is equal to 0. So the only thing I'm interested in is the imaginary part. And because I'm dealing with a fraction, if a fraction equals 0, it's got to be the top of the fraction that equals 0. So I'm actually only interested in the imaginary part in the top of the fraction. Minus x plus 1y plus x minus 1y must equal 0. Okay, now I can come up with an equation here. And I end up with simply y equals 0. So the x-axis. However, it will exclude 1, 0. That 1, 0 would not work because if you said z was equal to 1, look what happens to the actual function itself. We end up with 0 on the bottom of the fraction. And you can't have 0 on the bottom of the fraction. So I know I've got to exclude that particular point. Geometrically, if I did it this way. Well, now I'd be saying, well, I know the argument is either 0 or pi. It's got to be one of the two. Therefore, so the argument of z plus 1 on z minus 1 is 0 or pi. If I break that argument into two different arguments. So I've got argument of z plus 1 minus the argument of z minus 1 is 0 or pi. And we have to think about what this means geometrically. Okay, so here we go. Z plus 1. So the vector z plus 1 would be grab some random point z, join it up to negative 1. The vector z minus 1, same z, but now I'll join it up to positive 1. And the difference between the two will either be 0, they've got the same argument, or pi, they're going in opposite directions. So it has to be a straight line that goes through those 2 points. Because if they have the same argument or opposite directions, we must have a straight line. Right? So here's the situation here where I put in not the whole line yet. Right? So I'm going outside the 2 points. Well, these vectors are going in opposite directions. If it was in the middle, then the vectors would be going in opposite directions. The locus is y equals 0, the axis. But it'll exclude, hang on a sec, I've got a different answer. Because remember, when we talk about rays, you exclude the starting point. So I'm actually excluding 2 points here. Plus or minus 1, 0. Well, which one is correct? It's 1, 0 only. Always go back to the original question. You see, I changed the question into a geometrical thing. So yes, if the question was, find the locus of the argument of z plus 1 on z minus 1 is equal to 0 or pi, then both points would be excluded. However, that wasn't the question. The question was, w equals z plus 1 on z minus 1, and w is purely real. Now, if I substitute in, what was the extra point? Negative 1. If I substitute in negative 1 on there, I'll get 0 over negative 2, which is 0. And 0 is a purely real number. So it does work in the original question. Okay, find the locus of z if the argument of z on z minus 4 is pi on 6. So this is the one where I'm saying, hey, I see the argument, linear function on linear function equals an angle. I got an arc of a circle. Question is trying to work out where it is. And this is where geometry is far superior. Argument of z minus the argument of z minus 4 is pi on 6. Again, some random point z, if I join it up to 0, but also join it up to 4, then the angle between the two, or the difference of the arguments, will be pi on 6. Okay, so let's draw that. One, and there's the other. And you'll notice I've put it underneath the x-axis, and that's because I know what the final answer is going to be. Z turns out to be below the x-axis on this one. Now, how did I know that? It's like this. The argument of z must be bigger than the argument of z minus 4. You see, because when we take it away, we end up with a positive number. So I know that must be true. The reality is when I do these, I always assume they're above and then see if it works. So if it was above, so there's 0 and 4, so I'll just put it there, then it's a lot easier to see which one has the bigger argument. Now, in this case, the bigger argument is z minus 4. Well, that's not what we want. Therefore, it must be below, not above. Because when you go below, you're now playing with negative numbers. That's still a bigger angle, but it's a negative number. So you've got a negative small number minus negative big number. Minus minus is a plus, becomes positive. Okay? So as I say, I'll always assume it's above, just play with it and have a look at it and go, yep, no, works or doesn't work, and then I can work out whether I'm above or whether I'm below. Now, because I know this is going to be an arc of a circle, then the line joining 0 and 4 must be a chord. The next thing I notice, it's all about circle geometry here. The perpendicular from the centre bisects the chord. So if I want to find the centre of the circle, I know that the line from the centre will go through the midpoint of the chord. That's why I've now labelled in 2. It's the midpoint of the chord. But the perpendicular from the centre bisects the chord. So if I draw a line perpendicular to that, then the centre must lie on this line. Now the centre must be below the x-axis because I'm dealing with a major arc. I'm dealing with a major arc because pi on 6 is less than pi on 2. So if you think about drawing a circle, where's the centre? Well, if it's a major arc, it must be on this side of the chord. If it was a minor arc, then I know the centre would have to be on the other side. Okay. So I know the x-coordinates because I've got a vertical line. Now I've got to try and find the y-coordinate of the centre. Okay. Well, there's the radius. I'm going to need that as well. I don't know what that is yet, but let's just work it out. That's going to be 30 degrees. Now, how do I know that? Another circle geometry theorem. The angle at the centre is always twice the angle at the circumference standing on the same chord. So this is 30 degrees at the circumference, which means this whole angle at the centre of the circle must be 60 degrees. But in this right angle triangle, then half of that becomes 30 degrees. I've got enough information now, I think, to work out what I need. Y over 2 will be the tan of 60 degrees in that right angle triangle. So y is 2 root 3, but hang on a sec, I'm below the axis, so actually that y coordinate will be minus 2 root 3. So I have the centre of this circle. Now radius, I can now do Pythagoras, and I get that the radius is 4. Let's now describe the locus. Locus is the major arc of the circle, x minus 2 squared plus y plus 2 root 3 squared equals 16, formed by the chord joining 0, 0 and 4, 0, but not including these points. Not including? Well, if I was to sub 0, 0 in, then I'd get the argument of 0, because it'd be 0 on the top. Well, 0 does not have an argument, so that doesn't work. If I substitute in 4, 0, then the bottom of the fraction becomes 0, and I can't have that either. So both of these points are excluded in this case. Another way you could say that, still the same circle of course, but you could say, but it's where y is less than 0. So you might tell you what the range of it is. But you need to mention some restriction about that. 1f. Here's the interesting thing, though, with these functions. You are now dealing with 4 dimensions. You see, when you've got your Cartesian number plane, you're getting an x value, you're substituting it into the function, it spits out a y value, and we can draw a picture quite nicely. Now, what we're dealing with here, we can't visualise in our world, because we're inputting a number that has both a real and an imaginary part. And the output will be a number that has a real and an imaginary part. So there are 4 pieces of information to plot that point. Can't do that in our world. So what we tend to do is we have one graph for the input, one graph for the output. So when we were dealing with these functions, so let's just go back. So what we're basically saying is we're inputting all the numbers such that their modulus is equal to 4. So we're inputting, it would be a circle, radius 4. We're saying we're going to input every one of these values into this function. What picture would it produce? So we would have another Argand diagram for the output. And on the output we'd get, it's also a circle, but the radius would be a half and the centre would be 1. If we could draw a 4-dimensional graph, well then we could plot all the points. But as I say, we physically can't do that in our world. Welcome to the 4th dimension.